Welcome to Ants Tiny Builders. I'm your host, Pastry Chef Bear. Grab your magnifying glass because we are diving deep into the microscopic world to see how the most impressive biological architecture actually gets built. Down here at the millimeter scale, the physics of everyday life feel entirely different. A stray pebble or a clump of dirt isn't a minor inconvenience. It carries the crushing, inescapable weight of a massive boulder. Navigating this heavy terrain requires a highly specialized machine. Watch how this single worker ant approaches the obstacle. Notice the smooth, almost glass-like articulation of her joints as she sizes up a payload that dwarfs her completely. In an environment this dense, survival depends entirely on the ability to overcome raw static friction and gravity. Before any complex society can be established, the individual parts have to be capable of moving the Earth itself. To move that Earth, a worker ant initiates an explosive contraction of muscle fibers. She hoists a mass of solid, textured clay straight off the ground, holding it steady without buckling. This diagram shows exactly what that looks like by the numbers, a 1:50 weight ratio block chart. For a human, generating that proportional force equals walking up to a fully loaded commercial truck and deadlifting it over your head. A human skeleton would instantly shatter under that load, but the ant's exoskeleton distributes the extreme downward pressure across an interconnected network of rigid plates, routing the physical stress away from her most vulnerable internal organs. Millions of years of evolutionary pressure have pushed this biological hardware to its absolute physical limit. When it comes to raw, heavy lifting, the single worker ant is a perfected machine. But external strength requires internal fuel. To understand how this machine truly operates, we have to look past the heavy lifting and examine the hidden logistics network running inside her body. This cross-section shows the ant's internal anatomy, specifically highlighting the brightly glowing blue cavity. This is the social stomach. It is not used to digest her own food, but acts as a decentralized biological cargo hold designed exclusively to store and transport liquid calories for the rest of the colony. Even her structural joints operate as specialized hardware. Watch how the microscopic fibers of her neck lock together like finely milled mechanical gears. They align perfectly to distribute massive external loads safely, sparking with energy under the extreme stress. Every internal system is engineered for utility. Her anatomy proves she isn't built to survive as a solitary creature. She is a modular physical component designed to plug directly into a much larger empire. Yet, if you watch a colony on the move, that individual mechanical perfection seems to disappear. Millions of ants scatter in random directions, moving frantically without a designated leader or any obvious central command. They manage this chaos using a highly effective invisible software. Instead of taking verbal orders, they leave behind tiny drops of chemical signals called pheromones, marking the exact paths they walk. This top-down diagram shows blind scattering turning into a calculated route. Black dots move randomly through a maze, leaving faint yellow chemical trails. Shorter paths take less time, so they are walked more frequently. The signal reinforces and thickens, calculating the most efficient route. By continuously reading and updating these chemical trails, the swarm creates a self-correcting feedback loop. They navigate dense forests and complex terrain flawlessly, entirely bypassing the need for a central brain. Heavy lifting and clever routing work perfectly in a stable environment, but when flash floodwaters rip through the colony, neither individual strength nor chemical trails can stop the swarm from drowning. To survive, the ants instantly change their physical state. They latch their jaws onto each other's legs, densely interlocking their block-like bodies to construct a solid, geometric living raft that floats on the surface of the rushing water. The resulting superstructure is highly elastic. The interconnected bodies act as biological shock absorbers, bending and flexing with the turbulent waves to keep the queen and the brood completely dry at the center. In the face of absolute destruction, individual survival instincts are completely discarded. The ants surrender their autonomy, becoming nothing more than structural building blocks to ensure the colony remains intact. From the interlocking mechanical gears in a single worker's neck to the complex chemical algorithms calculating the fastest route through the forest, every element operates in total synchronization. This diagram illustrates that exact integration. We start at the individual joint, but as we pull back, the biological pathways map out to form a massive, fully autonomous data processing network. An individual's ability to lift 50 times her weight is a mechanical feat, yet that power finds its full utility when interfaced with millions of others to solve environmental problems in real time. I've been your host, Pastry Chef Bear, and I hope you enjoyed this look at the magnificent mechanics hidden right beneath our feet. Thank you for watching Ants, Tiny Builders. Natural selection has favored the development of the flawlessly integrated collective over the isolated strength of the individual.